I want to clarify what is meant by the elementary charge and then do a problem which has some chemistry connections. Don't worry, it'll be very short here. The pain will be only momentary. So we have the smallest unit of charge in nature being the elementary charge. 1.6 times 10 to the negative 19 coulombs. It's an electron or a proton. Symbols: E negative for electron, E positive for a proton, or just generalize it by calling it E. So that's the elementary charge. Now, this is a very small fraction of a coulomb. It's this many coulombs, the elementary charge. So an entire coulomb requires a whole bunch of charges, namely the inverse of that number. So 1 coulomb is 1 over 1.6 times 10 to the negative 19 coulombs per elementary charge. And what does that give us? It gives us the number of elementary charge per coulomb, which is 6.25 times 10 to the negative times 10 to the 18 elementary charges per coulomb. So what's that? Well, trillion is 10 to the 12, so there's 6 more orders of magnitude, so it's 6 million trillion elementary charges in a coulomb. All right, so now let's consider the following, namely a mole. Remember, a mole of a substance? Well, it's the atomic weight in grams, and that's also a certain number of particles of that substance. At 6.02 times 10 to the 23rd, that's right, Avogadro's number, that in the past, I'm sure, you've grown to know and love. Well, here's our example we're now going to consider. We're going to take 1 kilogram of pure lead, like the 1 kilogram lead bricks that you've seen, that I have. And let's imagine all the electrons in that kilogram are removed. They're deposited on the other side of the room. Now don't worry about the details of how we're going to do that. There is a problem, yes, but we're going to do that, and the rest of the object is going to be on the other side of the room. I might ask you, what has the lead become when we take all the electrons out? And you would correctly say, well, it's still lead, but it's fully ionized. Because what determines what the substance is the number of protons in the nuclei, right? So it's still lead. And a very tiny, a small fraction of 1% of the mass has been removed from the block in taking all the electrons out. But the point right now is, what would be the attraction force between those electrons and the lead brick? Very positively charged lead brick attracted to the electrons on the other side. So the answer to the question would be the electric force, and that's KQ1 Q2 over R squared. The object, the brick, and the electrons can be considered point sources for each other. And so it's KQ squared over D squared, because it's the same amount of Q on both sides. We can drop the subscript, and that's K cap Q squared over 100. I could go ahead and put the 9 times 10 to the 9th in, but we'll do this in a moment. What's obvious from this is that we need Q. So how do you get Q? Well, to get the amount of charge corresponding to all the electrons, consider that the atomic weight is...
Don't worry, you're not expected to know this.
That's right. 207. I probably won't test you on that particular number. And so that's how many protons and neutrons it has. And so the atomic weight, 207, corresponds to 207 grams for Avogadro's number of those particles. All right, 207 grams per mole. So how many moles does the lead brick have? Well, it's 1,000 grams of lead divided by 207 grams per mole gives us 4.83 moles. Therefore, we know how many moles we have. Let's go ahead and solve for the charge. The charge is how many moles times how many atoms per mole. It's a whole lot. Avogadro's number of atoms per mole. Now the moles go away. Very nicely. We're left with the number of atoms. Well, every atom has a certain amount of electrons, namely 82. Once again, you don't have to know that number. 82 elementary charges per atom. We now have the number of elementary charges. And we know how much charge an elementary charge has. It's 1.6 times 10 to the negative 19 coulombs per elementary charge. And so now we have left in our dimensions here the number of coulombs, which is 38 megacoulombs. 38 megacoulombs, that's right. So the electric force, continuing where we left off here, we now know what the charge is. 9 times 10 to the ninth, 38 mega squared over 100 equals 1.3 times 10 to the 23rd newtons. Get a handle on that number. How many tons is that?
Nothing in your experience helps you even to begin to comprehend the size of this force. But we know that long before this degree of charge separation is achieved, we have a massive equalization event, namely a bolt of lightning.
So there you have it. And that's about enough of fun physics for this little lesson.